Okay, morning everybody. Welcome to our live video about Vortex, because what we're going to be talking about today is the Vortex drill that's offered by Allied Machine and Engineering. My name is Rob Brown. I'm the engineering trainer here at Allied, and I have a special guest today. I've got Jamie Rosenberger, who's the product manager for the Vortex product, and she's going to be telling us about some of the applications where people are using these out in the field. So what we're going to do here first is we have a short conversation by Kyle about how to use Microsoft Teams to make sure everybody's logged in properly and you can do the comments and all those kind of things. So we'll play that video and then we'll get started with what the product is.
Okay, I'm going to go over a couple things with Microsoft Teams before we get started. At the bottom here, there's a closed caption icon. You can click on that icon and it will turn on subtitles. You need to have that gray bar highlighted for them to be on. If it's off, you will not have captions. If it's highlighted, you will. If you want to change the language, you click on the settings gear icon there, go to captions and subtitles. Click here and then choose your preferred language. And then you're going to be able to read subtitles translated for you in real time. At the top right, there is a question and answer panel. To open that, just click on that icon and then you will see this panel now, and the event will still be going on to the left. You have My Questions tab here where your private questions between you and the moderator will show up here, and then you have featured questions here that our moderators have posted publicly. To ask a question, all you need to do is type in your name right here, ask your questions in this box, and then you can either post it as anonymous or send it with your name. And then that will go to our moderators and they'll be able to answer your question. If your question is something that we'd want everyone else to see, we may publish that under our featured questions, so perhaps someone else may have that same question and it can be answered. So that's everything, just real quick and short. So let's get to the event today.
Okay, well hopefully everybody knows how to use Microsoft Teams now, so now we can get started talking about the actual products. So like I said, we're here to talk about Vortex, and just to kind of give you a little refresher on what Vortex is. It is our IC drilling system that is available in diameters from 11 to 47 millimeter diameter. 12 to 47. So that's why I got Jamie here to tell me what's going on. So that's about 7/16 or about a half an inch all the way up to 1 7/8 in inches. We have 5 different geometries that we offer, and they're broken down by ISO classification. So we have P for steels, K for cast iron, M for stainlesses and high temps, N for non-ferrous applications like aluminum, and then lastly we have an H geometry for hardened steel, so think like molten die stuff, things over 35 Rockwell, things like that. The links that we have available are 2, 3, and 4 times D, and once again they go from 12 to 47 millimeters. And just to take kind of a quick look at the tool, this one is a 26 millimeter tool. And if we go to our little overhead here, I can kind of show you some of the features of it here. Okay, grab my insert. Okay, so looking at it overhead here, you can see that it's got 2 IC pockets, but it actually uses the same insert for both pockets. So let me just slide this in and see I can use, this one is for doing the OD, or the major diameter of the cut. And whenever we're cutting on the center, we're actually going to lay it down, I'll get my thumb out of the way here, lay it down flat like that for doing the center. So I actually get 4 sides off of that insert, that same insert. So I'll use this, flip it over here, and then I can move it over to the periphery and put it in and use it as the periphery cutter on the outside. And once again, we have 5 different geometries available for your specific cutting application. All the tools have nice big coolant outlet holes on them and everything, so you get plenty of coolant flow. And the flutes are designed to evacuate the chips that get created. They're actually unbalanced, kind of hard to see here, but my periphery chip gullet is a little bit smaller than the center chip gullet because I'm going to make a bigger chip in the center, and I'm cutting to center. Just taking a quick look at the inserts that we have, like I said, they are 4-sided. So when I'm doing the center cut, I'm going to be this way. When I'm doing the periphery cut, it's going to be like this. And you can see I got my geometry out here for doing the periphery cut, so it makes a nice little chip. Whenever I'm doing my center cut, what I have here is a cutting edge that's really strong to be able to handle the zero surface footage at the center and the increased cutting forces at the center of the cut. So that's just kind of like a general overview of the Vortex product. And what we have today is we have a couple of live demos that we're going to run, and we have a demo or two that we're going to show you that was actually pre-recorded. The first one that we're going to show you is using the Vortex drill to do plunge milling, because that's a pretty popular thing and it can handle the interruptions really well. So what we did was we took a 4-inch diameter slug of 17.4 pH stainless, it's about 32 Rockwell, and we actually went in with a 13 millimeter Vortex 2x-D, and plunge mill it about 1 inch deep, and we did a succession of different things and ended up making about 1.5 inch diameter hole in the center. So what we're going to see in this video is the plunge milling application, and the reason why we ran it as a video is because it takes about 5 or 6 minutes to run, so we're going to condense it down, because once it does the first couple of holes you kind of get the point of what it's going to do. So the speeds and feeds this is going to run is going to be 350 surface feet a minute. The first drill, when it comes in and just does straight up drilling, it's going to run 4 thou per rev. Whenever it goes to do the plunge drilling, we actually have to run about 50% of the feed rate that we would for the initial hole, because of that interrupted cut that it's going to do. So it's actually going to run at 2.5 thou per rev. So we're going to watch this video and we're going to kind of see what it does, and we actually have some parts that we made here to show you what the chips look like, what it was before the end mill came in, and then after the end mill came in and cleaned it up, and it's for doing like pocket milling. So we're going to play that video for you now. So once again, this is 17.4 pH stainless, about 32 Rockwell. You can see over on the left-hand side there, we're running 350 surface feet per minute. This first hole is going to be at 4 thou per rev. Okay. So it goes in and it drills the hole, and then what it's going to do is just go and start to open this up in succession. And this is the part where we're going to speed it up after it does the first couple of holes. But you notice our feed rate went from 4 thou per rev to 2.5. The reason we do that is because since we're in an interrupted cut, we want to run a lighter feed rate to reduce the bending forces that are going to be presented to the tool whenever it goes. And so now we're going into high speed mode here, so you can kind of see this thing running at a sped up pace, because once again, if we were to do this live, you can see we're now about 2.5 minutes into this application now, and we're not done yet. Now, running through the tool with this was 300 psi of water soluble coolant, and this was done on a Haas VF3 machining center. That's about a 30 horsepower machine. And that's actually what we're going to be doing for the demos that we run the rest of the time here. So you can see he's coming in and doing that last cut, so you can see that come in, and then we're going to come in with an end mill, and we're going to run, well, you can see here what it looks like when it's got the plunge cuts done to it, and then we're going to go in and come in with an end mill and take those pockets and turn it into a circular pattern instead of having those the cuts. Okay. Now I will tell you, this is just a 1/2 inch end mill we went and got out of our tool crib. This is not running at a speed and feed that's maybe optimized. It's just to show you that it can do it. As you can see, we're only running 98 surface feet and 8 thou per rev, and we're running it basically dry, so you can see the tool go through the motion. Okay, so there's the end cut. So in a grand total time of about maybe 6.5 minutes, we created this pocket mill. If we were to do this with an end mill, it would take a substantially longer amount of time. So to look at what we've done here, we're going to let Jamie talk here for a minute, but here is what it looked like with the plunge mill.
Yep.
So Jamie, go ahead and take over.
Yeah, so applications like this would be really beneficial for some examples would be like gun industry, if you're going to be milling out a pocket, and it doesn't have to be just a pocket where, you know, it's circular. It could be elongated, really coming in those situations. A lot of times, typically, you would maybe plunge a couple of spots and then really hog out most of that material with an end mill. That's going to be just cycle time killer for you, and that's where you start to add up with the cost of it. So having the Vortex come in and be able to really hog out the material very quickly and then finish it up with an end mill is a cycle time saver for you. These applications, running an IC drill that can handle those interrupted cuts is going to save you cycle time and ultimately money. So there is the Vortex plunging it, and then you can see the finished product. You can see how nicely that cleaned up. Like I said, it doesn't have to be a circular pattern. It could be anywhere you're trying to remove a lot of material. An IC drill is going to be great to get you started, step over, and then be able to really remove that material quickly. Here's the chips from the Vortex. You can see how nice and small and broken up the chips are, not causing any problems at all. and this was in stainless, so this is really nice.
So the only thing I want to kind of point out to you is, we can go back to that overhead for just a second, is while we were doing those plunge cuts, you can see how clean the surface finish is. Now, granted, in this application, what we did was we cut all this away anyhow, but this just shows you how well the Vortex does in this fairly significant interruption. This was what was the step over on this, Dave? 60% step over. So we were doing a majority interruption when we were doing this, but we were still getting a nice, decent surface finish on the inside of this. So what that kind of boils down to is, even if I wasn't coming in to use that milling operation afterwards to clean it all up, if I need to do those step overs for some odd reason, for whatever my part quality is, the surface finish at the end of the result is actually quite good.
Yeah, and even situations where you're going to be on a steep incline, Vortex has no problem biting right into that. You don't have to come in and mill out a surface and then from there start drilling. You're able to just start off right with the IC drill, the Vortex, and just come straight in, and once again, it's a cycle time saver for you. So any inclined surfaces, interrupted cuts, surface finish still maintains to be really nice.
Okay. Thank you, Jamie.
No problem, Rob.
All right, so what we're going to do next is we're actually going to run a live demo here. We're going to run some A36 material, because another not super common thing that gets used with the Vortex product, but somewhere where we found that the industry has some interest in a product like this is running in structural steel industry, where they're drilling larger holes in I-beams and plates and that kind of thing. As you may be aware, Allied actually has a structural steel product line that we make both for the TA product and the Genesis product. The size range on those goes from about 1/2 inch up to about 1 9/16. But if somebody needs a bigger hole in that, that's where the Vortex drill is going to be pretty useful for doing this. So what we're going to run here is we're going to run a 47 millimeter Vortex drill that's a 2x D drill. We're going to run into some A36 material that's 1 inch thick. So 47 millimeter, which is about 1 7/8" pretty close. And we're going to be running in, once again, A36. It's about 140 Brinell in hardness. But what's common in the structural steel industry is to run an air mist instead of standard flood coolant like what you would normally see in a Haas machining center. We actually have a mister hooked up to this. So what we're going to run is an MQL system. So it's going to be running predominantly air. It's about 90 psi of shop air, and then it's just got an atomized mixture of the fluid mixed in with it for lubrication purposes. So it's really almost like drilling dry, okay? But that's real common in the structural industry. Where we're going to run this tool is 275 surface feet a minute and 2.5 thou per rev. So we're going to run that. We're going to gather up some of the chips to show them to you. We'll actually pull the slug. It's going to be very hot, so you'll notice whenever Tim's pulling them out, he's using a glove because I don't want to be touching these things. So Tim, if you're ready, we'll put our glasses on. Once again, this is A36 material, 47 millimeter diameter. You can see on the screen there, we're running 275 surface feet a minute, 2.5 thou per rev. Metric equivalent for that is about 84 meters a minute and about 0.6 millimeters per revolution, okay? Once again, this is on a Haas VF3 machining center, but we're using it like it's going to be a structural steel drilling machine, okay? Because that industry does use specific machines for doing this kind of work that we don't have, so we're just kind of emulating what's going on here, okay? So you can see it's making a chip, and we'll take a look at what the chips look like whenever it comes out, okay? But it gets very hot in there. You can see the smoke at this point already. And we should be just about ready to break through. And our spindle load looks like it's about a steady 28% as it's going through there, okay? Now we're starting to break through on the bottom, okay? Should hear a little bit of a chirp on breakthrough, okay? And whenever that's done, we'll gather up some of the chips and take a look at them, okay? Now, once again, remember, this is running predominantly shop air, running at 90 psi with a little bit of oil mixed in with it. So it's a pretty hot application to run. So we got to be careful as we gather up the chips to take a look at them. But we'll gather them up, take a look, and see what they look like.
And another thing to note is the feed that was ran on that, the feed is really low because that's what's typical on these machines, but we're still able to make a chip even at those lower feed rates, where typically on a, we're going to say a pointed type of drill that you would use in structural steel applications, you would need to run a much higher feed rate to be able to form a chip. So having an IC drill that is really designed to be able to run at that lower feed rate and still make a chip makes for a really successful application in the A36.
Okay, so let's take a look at the chips that we made here. Now remember, this is running basically in a dry situation, and these chips are still hot, so stay back, Jamie. Okay, but you can see the discoloration that we have here, but that's going to be because of the fact of the heat that's generated while it's cutting. Okay, these chips here are going to be what's done with that outboard insert. Okay, so that's what's being created here. This is what the center chip is, and with the Vortex drill, the fluting on the Vortex drill is actually designed to handle this large center cut chip that gets created. So it's not going to be any kind of problem, except for the fact that today it's still probably about 200 degrees, so I'm not going to touch it. But you can see the chips that we created, so it makes a chip. The load on the machine was pretty light. You know, once again, it's a 30 horsepower machine running at that, what speed was it again? 275 and 2.5, and it used 28% of the spindle. So here's my surface finish that I get out of it. It's actually a nice smooth finish, which is pretty good for this type of material, because, you know, A36, it's got car bumpers in it and all kinds of messy stuff. It's a really dirty material. So the way that it machines generally isn't really good. It tends to tear a lot, but the Vortex actually makes a nice clean cut in this. So it actually looks pretty good. Now I wouldn't exactly say that's like a ream finish, but for that type of material, it's like a ream finish. That's really good. Okay, so I need to wipe my hands off here real quick. And we're going to talk a little bit about the fact we have another video that we actually have a company by the name of Flexarm that's over in the western side of Ohio, and they actually make beam drilling machines, and actually were kind enough to send us a video of the Vortex product running a couple of different diameters on their machine. Okay, and so we're going to play that video for you here real quick. It's just about a minute long video. It's not terribly long, but it'll show you actually running on a machine that was built to do this kind of work, as opposed to running on our Haas, which we're trying to retrofit it to kind of show you what it does. Okay, so we're going to queue up that video here, and I'll just kind of walk you through what they're doing with it. Okay. It's a lot different than what we got going on. They're actually running into square tubing here, and you can see those hot chips coming off. That kind of sparking that goes on there is what it's kind of called in the industry. Once again, you can see that they're running the same mister system like what we did, but theirs isn't nearly as wet as ours is. So that's why those chips are getting really hot like that. This, quite frankly, is just a really extreme application of using a cutting tool in a steel drilling application, but it's common to that marketplace. Okay. So once again, this is a 26 millimeter diameter. The depth of the cut is about 3/8 of an inch. Okay. And they're running 803, and you can see once again that surface finish is actually quite nice, considering the fact that for all intents and purposes it's basically drilling dry. So now they're doing the second application, and this one is a 34 millimeter diameter, and it's running 600 surface feet and the same 3 thou per rev. Okay, so once again it gets kind of hot in there, but this is a size that starts to get a little above like what we would normally have offered as part of our structural steel drilling line. So using a tool like this would be pretty good. And you can see they're running at 5 inches a minute penetration rate with this too. So that was once again a 34 millimeter diameter, which is just a little over 1 3/8. Okay. So for the last application, they're going to run a 45 millimeter diameter, which is about 1 3/4. Okay. Running it at 550 in 3, okay, or about 167 meters a minute, 0.8 millimeters per revolution. Still 4 inches a minute, they're on the 3/8 of an inch deep, okay. So this is running a much larger hole than what we would have available as part of our structural steel line. So if the customer needed to do large holes like that, they could certainly do it, okay. So once again, this isn't a situation where we want to sit there and tell you that this is specifically built for structural steel machining, but it is a product, it's kind of an accessory area where we can use a tool like this that maybe you didn't think about using it there before.
Well, let's talk. Can I talk real quick about the perfect storm of structural applications? The material itself is gummy for the purpose of what it's intended for. Problem with that is the machines that you actually can drill these holes on are open, so you end up having to use a mist or air because you can't have normal 300 psi or even more coolant. You just can't have that in an open type of machine. So now you've got a material that's extremely gummy, and then you start to drill with little coolant, you start to induce a lot of heat. Heat is ultimately going to give you a situation where you're going to have longer chips. Those chips won't break near as easily, especially in that type of material. So on top of it, the fixturing of these types of machines doesn't always allow you to run the feed rate that you need to in order to help break that chip. So what ends up happening is you ultimately end up with a elongated chip that it's a difficult battle just because of the situation. With the Vortex and having a geometry like this, once again, you can run that lower feed rate and be able to still break a chip in that material. But you got all things fighting against you in these applications.
Yeah. And obviously, tool life's going to suffer because of the fact the tool's getting really, really hot whenever it's cut. But once again, that's the way this marketplace runs, and they're used to it. So if you're doing beam drilling, then none of this is like big news to you. But if you've never seen it before, it is quite a bit different than standard machining. Okay. I just want to give you a little bit of background. I didn't really talk about the flex beam machine that we just ran on. Just to let you know, it's an 18 horse machine. It has a 3,000 RPM spindle on it. And it has capability, as you can see by that schematic that they showed us at the beginning. You can do beams that are multiple feet long. I don't know what the exact length is, but if you have interest in the machine, by all means, contact our friends at Flexarm. And I thank them for providing us with that video so you can see how it's going to work in a real world application as opposed to us trying to recreate that here in our lab.
Yep.
Okay? So moving on back to more traditional machining applications, okay? One of the things that's another common issue that we find out through our applications group and our FSEs and whatnot with the Vortex drill is the proper application of the right insert, okay? As an example, we're going to run a piece of 1018 here in a couple of minutes, about 170 Bernal in hardness. Now, going back to that tool selection process, okay, it's using that ISO call out. So the first insert that you would be inclined to grab a hold of would be that P geometry insert, which is designed for steel applications. Okay, based on the machining characteristics of 1018 though, it likes a little bit more scoop going on in the chip whenever it's going on to try to make better chip formation. So if you look in our catalog at the book recommended speeds and feeds and what tools we recommend, actually for this softer 1018 like what we're going to be running here, we actually recommend the M geometry, which would be for stainlesses and high temps. Because the differences between the M geometry and the P geometry is significantly the rake angle that gets presented to you. When we talk about chip formation, the things that we can do as a tooling manufacturer to give you the chip that you want, the main thing I'm going to do to drive that is the rake angle. A steeper rake angle is always going to make a better chip than a slighter rake angle. So the more positive the rake is, the better the chip form is going to be. And the P geometry does not have as high of a rake angle as what you have with an M geometry. So even though the M geometry is designed for stainlesses and high temps, we're going to use it in this lower carbon steel because that higher rake angle is going to give us better chip formation. So whenever you look in the Vortex catalog, we actually have that recommendation page, and you'll actually see in softer materials like the 1018 that we're going to be running, even though P would be the one that you would think would be the one that you're going to run with, you're actually going to run with an M geometry. So just to kind of show you that, what we're going to do is we're going to run a 26 millimeter Vortex that is a 2x tool. We're going to run it into some 1018 that's about 170 to 180 Bernal in hardness. We're going to run all the way through, so it's going to go 1.5 inches deep. And by the way, 26 millimeters is about 1.024 inch, so it's just under 1.32 inch diameter. Okay, speed and feed we're going to run at is going to be 700 surface feet a minute and 6 thou per rev. In metric, that's about 213 meters a minute and 0.15 millimeters per revolution. The coolant that we're going to use is going to go through the tool again. We're going to run regular coolant at 300 psi coolant pressure to show you how that is going to help with that. And what we're going to do is we're going to drill 2 different holes. We're going to run P geometry first. We're going to gather up the chips and take a look at those. And then in the same piece of material, we're going to go beside that. We're going to run it the exact same application again, same speed and feed, same diameter, but instead of using a P geometry insert, we're going to use an M geometry insert. Okay?
A36 would be the same way?
Yes.
So in those structural applications, same thing. You would want to go with an M geometry to help break up that chip since it is so ductile of a material.
Okay, so this is going to be, I'm going to start off with the P geometry. Okay, and remember, we're going to run the same speed and feed with both of them. So it's going to be 26 millimeter diameter, 1.5 inches deep. Okay, 1018 low carbon steel, 170 to 180 Brinell in hardness, and running 706. We're going to gather up the chips that we get. This is the P geometry. What's our load, Tim? So the load was 70% on the machine, because when we run the M geometry, since we're going to run same speed and feed, same material, everything, we're going to look to see what difference that makes to the spindle load as well. Okay, so I'm going to get some chips here from my buddy Tim, see how that works out. And then once we're done running the M geometry as well, we'll go ahead and show you if there's a difference in the hole quality. Okay, so here's an example of the chip that we're getting. You get these weird ones, like this is actually an entry strainer, because you can see where it starts at nothing and goes to something. And then here's the chips that we get. Okay, now what I will tell you is 1018 is a finicky little bugger, and we can end up with a myriad of different chip forms out of it because of the inconsistency in the material. I got to be honest with you, the chip form we got on this one here is not terribly bad.
Throw in a different slug and it may change.
Yes, or if I drill it in a different position, it can change a little bit
absolutely.
as well. Okay, so now what we're going to do is we're going to run the exact same application again, same speeds and feeds, but all we're doing is we're switching from a P geometry insert to an M geometry insert. Okay, so what we're going to pay attention to is the difference in chip form that we get, if we see any, and then also the difference in spindle load, because it should run at a slightly different spindle load than what we got with the P geometry tool.
Yep, just changing that shear angle and letting it get up under the material a little bit more instead of pushing it.
Okay. So while Tim's kind of clearing the chips out there, so we make sure we're not grabbing any P geometry chips to show you with the M geometry stuff. Yeah, we're going to make sure the machine's cleaned off so we can show that to you. And he's got to do his tool change. So a little bit of background noise while that takes place. There we go. So once again, we're going to go and we're going to run this, and whenever we're done, we'll pull that slug so we can show you the difference between the surface finish, if there is any difference in surface finish between the two. Okay? So here we go. So now we're just going to run the second hole. Same speed and feed. Okay, so what's my load on this one, Tim? So it's 68%. So there was a slight difference in the load that was on it. I wouldn't call that statistically significant.
Not a game changer.
But it is a little bit different. You should notice a difference anytime you change the geometry.
And once again, with 1018, like he said, it is very finicky. So we throw in a different slug, and you never know what's really going to happen with 1018. And of course, if you guys are machining 1018, you are already really familiar with this. One other thing we should mention is that we do have 2 application engineers in the meeting right now, so feel free to chat them any questions that you have about an application that you have.
Okay. There we go, kind of spread them out a little bit. Yep. This is actually a center chip. It just hasn't got wound super tight.
Yep.
But you can see the chip form on it, my opinion, is practically the same.
Yep, practically the same.
Now, once again, we get into this kind of fun whenever we're talking about 1018 low carbon steel, because it does kind of act however it wants to act.
Yep,
so,
absolutely.
But we'll take a look at, and you can hear Tim's back there cleaning the part off right now, so we'll get that from him. And I'll kind of pop that under. So, let me show you here. Try not to bump the camera. This is the P geometry finish. Okay, this is the finish that we get with the M geometry. Okay, now my professional profilometer here is telling me that they're about the same finish. But the thing to remember whenever we're talking about low carbon steel like that is it does have a tendency to want to tear instead of cut, so it's not super clean whenever it does come apart. So the fact that the finish on it isn't substantially different, quite honestly, doesn't really surprise me all that much. So
yeah, but the main point for this was not to get extreme results, but to just help everybody understand that just because the material that you're machining is an ISO class of steel doesn't mean you have to go with the P geometry. Those more ductile materials are going to need more rake to get up underneath that material and to help form a chip. So highly recommend using an M geometry, especially whenever you get into 1018s, A36s, just those gummy materials that are more difficult to form a chip. M geometry is really the way to go.
all right. So that's all we got for the demo portion of today, but I think Jamie wants to talk to you a little bit about some of the applications that we get into with this and those kind of things, right?
Yeah, so back to, one of the things that we were at the beginning, got a chip stuck to me. So Kyle, if you want to show this part again. So one of the things we were talking about at the beginning, so we'll just do a recap on some of these applications. In this type of an application, this is going to be great whenever you get into, like I said, gun manufacturing, even mold and die, anytime you're doing pocket work. Coming in, if you were going to mill all of this out with an end mill, it's nothing but cycle time. Being able to come in and really remove a lot of material quickly and then finish it up and clean up the edges all nice, because I'm sure you don't have a part that needs that kind of profile. Maybe you do, but it is nice to be able to really remove that material quickly in a lot of applications that you may have. So keep an eye out for applications where anybody's just doing a lot of end milling work to really remove a lot of material in some sort of a pocket. That is a great target application for a Vortex IC drill.
So what kind of applications would be doing that? Like mold making,
gun manufacturing. We've got customers that are doing receivers for guns that come in and mill pockets out, and it's just a cycle time saver. So a lot of times if somebody's got, we're going to say, more of a channel that they're trying to come in and end mill, just come in and drill 5 times, 6 times, whatever it may be, sidestep it over, hog that material out, and then come back in with the end mill and clean that up. Those are target applications where this tool really shines. Okay. The other one, the structural steel applications, we talked about that just because larger diameters on structural steel types of machines, they can be more difficult to form that chip. Once again, running at lower feed rates, ductile materials, you need to be able to still form a chip at that low feed rate. Vortex IC drill, that's really what it's intended for. And circling back to the first application, that plunge drilling, we talked a lot about where milling out a pocket, but the other thing that we really didn't highlight a whole lot is how well it does on just any type of interrupted cut. Coming in on an inclined surface, coming in on the edge of something, maybe coming in on the peak of a part, any type of interrupted cuts, the Vortex does really well just because it doesn't have a point. It's not looking for that point to grab into the material, and it's able to just start cutting as soon as it lands into the part.
Okay. Convex or concave applications?
Yep, convex, concave, absolutely. Coming into the side of a tube, we've got customers that, they maybe a 6-inch diameter tube where they've got to punch a bunch of holes around the outside, come in with a Vortex, and almost in a structural type of application, but in a circular on a tube, those end up working out really well.
All right. So the last thing that I really have to share with you today is, what we ran today are some unusual applications for the Vortex drill. If you haven't already signed up for it, we do have Vortex videos and instruction and everything on our Allied, what was it called again?
The Tool Academy. Allied Tool Academy.
So if you haven't signed up for that yet, go ahead and sign up for that. You can see the Vortex run in more traditional applications, and it'll kind of reinforce what you see here. The cool thing about the Vortex is it isn't used just specifically for just drilling a straight on hole. I can do slot milling with it, that kind of stuff. By going and doing the rough cuts, come in with that end mill and clean it all up. As Jamie said, doing mold and die work, receivers for guns, things like that. A lot of people come in with just an end mill and either circle interpolate it out or just plunge mill it, then come in and clean it up, and it's a very time-consuming process. So by using the Vortex to do all that rough work, you can get it down to where all I got to do is come in and clean it up whenever we're done. It's a huge time saver for you.
Yeah, so that's an easy one to become a hero with. You spot those applications on the shop floor, somebody's end milling a little bit too long, come in, hog out the material, and then finish it up.
Yep. So remember, Allied Tooling Academy, if you haven't signed up for that yet, you get to see my ugly mug on there quite a bit. We're going to have to get Jamie to do them because she's got a much more, I have a face made for radio, she's more set up for TV. So that's really about all that we have for today though. So thank you for your time.
Thanks for joining.
And if you have any questions, once again, we do have the application engineers online where you can do online chatting, or by all means send information to our application engineering group. They'll be more than happy to help you. Outside of that, thank you for your time. Have a good day, and we'll see you again soon.